started. So welcome back to the session. So this is the last keynote and also last session of the main BMVC conference today. So I'm TK from Imperial College, and it's my big pleasure, honor to introduce Professor Lama Chellappa as our last keynote speaker. So Lama Chellappa, I mean, if I really name only few out of his long list of careers and achievements and awards and fellowship too. He's a distinguished professor at Maryland, University of Maryland, and he's a recipient of NSF Young Investigation Award, and he got 4 IBM Faculty Development Awards as well. He also got KSP Prize from International Association of Pattern Recognition, and where he got tons of Technical Achievement Award from IEEE, and he was editor-in-chief in Transaction Zone PAMI, Pattern Analysis and Machine Intelligence, and he's a Golden Core member of IEEE Computer Society, and he's a fellow by IEEE, fellow by IAPR, also OSA, AAAS, ACM, and also AAAI. So that's just a teeny bit of his long list of such prestigious. And then if I share just some bit of my personal view, how did I find Lama in the field? So Lama is such a figure, I mean, meaning huge to me, and also I'm sure that this is to many of us in the community, where he is recognized as one of the best experts in face recognition. So I began my own research career in about 2002 on the topic of face recognition. So I started it by studying Lama's papers. For instance, like Bayesian face recognition, discriminant analysis. Also, the survey paper on the topic has been extremely useful to many people who started studying that back at that time. Also, when I checked his publication list, well, I'm really truly amazed that those careers, legacy goes very, very early, up to 1980s, not like 2000 when I started my research for myself. So, well, in fact, regarding his such earlier work, I'm a bit too young to confidently explain. But if I use some few examples that I see objectively, so it seems he got his first papers in 1980, and on the topic of Markov random field and random field model of images. And I know that this has become hugely popular topic, maybe in around the year of 2000, and lots of researchers and big names and students were studying this topic, MRF and CRF and their application to computer vision. But then Lama did this already in 1980, so that's about 20 years early. And so such pioneering his works were. Also, some other topics that he also pioneered in his research include activity recognition and motion analysis and biometrics like gait recognition as well as face recognition. Well, that's about his kind of his research in the past. But then, well, I heard him at some previous occasion that he himself said he's active past. So I very agree that he's one of the 3 most active members of the community, though I disagree that he's the past. So he's General Chair of CVPR 2017, so which was just last year in Hawaii. That's the biggest computer vision conference except this year. And he also chaired CVPR 2012. And the very first CVPR he chaired was back in 1989. So if you know that CVPR began in 1983, so Lama chaired one of the very first CVPR and also the latest CVPR in the last year. So we have about 30 years time gap between the 2 CVPRs Lama chaired himself. And so he's such a figure who has come through that time period of about 30 years and very active, and he has been doing such impactful research work. So when I read his keynote talk title and also abstract, I'm really excited to hear about it. It seems like such important aspects and missing directions in our deep neural network research. I'm sure that now many of us are doing our research on that. So yeah, that will be the key things that we might pay our attention to. And So yeah, those topics that Lama is willing to talk about and those concurrent topics that we are currently doing. So it will be excellent keynote I'm expecting, and I'm sure that you all will be. So let's welcome Lama Chelapadan.
Thank you. Thank you very much for a beautiful welcome. Never felt older. That looks like I've been doing research since 1980. Well, that's all right. Actually, I have my great students here. You have a student, you have a grand student, and then you have a great grand student. I met them yesterday, and one of them has actually finished PhD and is a faculty at IIT Bombay. There you are. So they took a picture with me. I felt like a great-great-grandpa, But we always felt, if you're working in computer vision, we never thought you could solve the problem. So we thought it would be a long ride. So for most people who are working in computer vision, it was at least a 40-year adventure, and nothing much would have changed. Except from 2012, things are all on fast track. I wonder why. That's what I want to talk to you about. I made this title because one of my recent students, Maya Kapkap, who's now at Waymo, was looking for a title, and I said, she really did not work on the core deep networks, in terms of developing detection algorithms or recognition algorithms and so on. She was more interested in the peripheral issues of sampling, how to sample from the training data set, and how to learn from compressed images, noisy labels, how to protect deep networks from adversarial attacks, and so on. So I consider them as very important issues. So I told her, well, maybe you can call your thesis as Learning Along the Edge of Deep Networks. So she really loved it. So I said, maybe it's a good title that I can use for this talk. I know you must be all very exhausted. This is the third day of the conference, and so I'll do my best to give a good talk. Historical comments, those of us who have been around, have different reactions to the reemergence of deep networks. I'll briefly discuss that, and then I'll talk about where we are. Of course, before I get to the issue of addressing, the sample issue, the security issue, and the generalization issue, and so on, I also want to give an example of a system we have built over the last 4 years, face verification, identification, subject-specific clustering, detection, and all of that, and just to show you why there is so much excitement about deep networks. Although we all know that it has warts and it has all kinds of issues, but for some problems, it's really producing results that we didn't think would be possible. So I want to share those results, and then, of course, talk about the core topics in the abstract, and then I'll talk about some open issues. So, I was at USC as a young assistant professor in 1981. I joined. In 1982, we had the Hopfield network. So it created so much enthusiasm that an optimization problem like traveling salesman problem could be used. Could be solved using neural network kinds of approaches. And then it took about 5 years for the first conference to happen in 1987 in San Diego. I was not involved in it, but it was nearby. So they expected 500 folks to come. 3,000 showed up. So for the next 10 years, everybody was doing neural networks, 3-layer networks for all kinds of problems. OCR was a dominant application, but there are many other things that were tried. For example, Dean Pomeroy's autonomous driving demonstration from Pittsburgh to San Diego was using a simple neural network, and it was 95% on its own. And of course, Tommy Poggio used it for face detection, and then a lot of OCR work in NIPS and so forth. I was interested in neural networks at the time through Markov random fields, Boltzmann machines, and so forth, so we did some work. And then we wrote a first paper on face recognition in CVPR 1992 with Van der Malsberg, and he was proposing an architecture known as dynamic link architecture. Some of you may be familiar with it, and it had hierarchical neural structures to it. but very small data sets in those days. And we also looked at CNNs for ATR. We only used a 5-layer network, not a lot of training samples, so it didn't give good numbers compared to other methods that were around at that time. For example, learning vector quantization. So, we kind of dropped it. But one thing about being in academia, even if you don't produce good results, you can write a good paper. So we did write a paper in 2001 CVIU and about this. But then, Jan LeCun, has been steadfastly pursuing LayNets and its variations, and of course we all know about AlexNet. I like to say the life of a computer vision researcher has not been the same since 2012. Before that, we were a boutique group telling everyone how difficult the problem is and how we can't find solutions for another 100 years. And that was a good thing to say because funding was good. And we were just continuing and writing good papers and going to nice little conferences. When I did CVPR 1989, it was 350 people who came. The 2017 one had 4,000 plus, and of course 2018 had 6,000 people. So we don't know how to react to these things. It's like suddenly you won a lottery, right? $100 million, and you don't know how to spend the money, and Anyway, so 4 years ago we were tasked to build the best face matcher recognizer. So we started that. It's a multi-university effort. UMD is the lead. We have CMU, Deva Ramanan, Columbia, Shifu Chang, Rutgers, Vishal Patel, he's now at Hopkins, and Venu Govindaraju from Buffalo, Terry Bolt from UCCS, and Alice Watul from UTD. So it's a very tough task. Extremely high levels of performance were anticipated. But at that time, deep networks had not really become the main thing yet, and everybody was aware of it. But suddenly, within a few months, everybody was started doing deep networks for solving this problem. So I'm going to very briefly discuss this system and kind of tell you where we are. And honestly, I've been working on face recognition from 1992, and I never thought this performance would be possible, right? So that's why I'm kind of excited to share that with you, and we have written many papers on this. So we introduced the notion of multitasking, so that we can do face detection, fiducial, gender, age, and etc. in the same network, and I'll explain to you how that works. And then we realized one of the things that you think when you are in computer vision is that 3D is very important, 3D models, right? Well, that is true. We spent a lot of time building 3D models from images and videos and so on. So we expected 3D models would also be useful here for us to generate a lot of face images corresponding to different poses, illuminations, expressions, and so on. But within a year, we realized that we need not really use any 3D models, because oftentimes when you have very difficult gallery images, trying to build 3D models from there is just not going to be very good, especially in surveillance situations. So we decided to drop the idea of 3D models, just use multiple networks that just works on 2D images, but the training data, spans over possible variations. And of course, we are not Google or Facebook. We have very small training data sets. We started with MSM. It's about 10 million, a lot of noise, so we curated. We are about 5 to 6 million face images we have to train. And of course, they are all celebrity images and so on. Some of you know. We don't have the 200 million faces that Facebook talks about in their 2014 CVPR paper, or 500 million faces that Google talks about in their 2015 CVPR paper. But it's another interesting thing. Our competition is big companies. If they also work on LFW and you work on LFW, and if there's a lot of data, their numbers are going to be better. And then our template size is very small. We do sublinear research, so we can search over hundreds of millions of faces. And and also implications in forensics. We have a PNAS paper in May 2018 in collaboration with Alice Watul at UT Dallas and Jonathan Phillips at NIST, where our algorithms were compared with forensic matchers, super recognizers, and so on. And there's an interesting comparison of performance, which kind of led to the conclusion they can take one of the best networks from our lab, and the forensic examiner can combine and fuse their results and get very high results on black box tests that are run for evaluating algorithms in this context. So the UMD system is looking like this. We have input image. And again, in this project, we don't know that we will, what kind of medium we'll get. It could be a single image, multiple images, could be surveillance images, videos. So we have the notion of template. It's no longer just an image, right? So, of course, you have to detect your faces. And till recently, we were using something known as ultraface. I'll describe this in very, very briefly. The most recent results we have produced, they come from an extension of the standard SSD, giving it a deep pyramid structure, adding it to it, because we also have to, handle tiny faces. As you know, Deva Ramanan, who is in our group, has been working on that. When you have surveillance kind of data, the face sizes can vary a lot. So we need to bring in this deep pyramid structure into SSD to make that happen. And then we do alignment. And another thing also we thought going into this effort is video. When you do have face recognition or verification in video, you have to use the temporal information. But I've written some papers on that way back in 2002 ECCV, I believe. But now we didn't even use that. We just got our deep features on a frame-by-frame basis, aligned them and flattened them, and that works well. Of course, that's not going to be very effective for the other project we are working on, action detection, but at least for face, I don't know how far we will succeed by ignoring temporal information, but so far we have not suffered much. So ultraface, as you know, you have to do the alignment before you can extract features when you deal with faces in the wild. So typically, and also if you have age information, gender information, these are very useful when you're searching over large data sets. Typically, we design different networks, different algorithms for each of these tasks, because gender detection, you can view it as a two-class problem, and pose estimation, fiducial, etc., as a regression problem. So one would ask for different loss functions for these things to work well. So then we also realized that not all these tasks have a large training data set. For example, for age estimation, the training data set is much smaller than what you would get for face detection. So we said, why don't we do a multitask learning framework so that we can do all of them using a single network, and so these help each other. It's like a bunch of students, getting Starbucks latte and sitting together the night before finals and studying hard, and everybody helping each other, hoping that they will all get A. Right? It does work sometimes. So we use the different loss functions. For regression, pose, and so on, we use the Euclidean loss functions. For the two-class problem, we use the cross-entropy loss function. As you can see in this table, the training data set that we have used varies widely across the different tasks. And again, if you are using a deep layer, like 101 layers and so on, one can actually look at the different layers and see how generalizable they are, how useful to share features across the tasks and so on, right? So that is the advantage of having these deep layers, and so that we are exploiting that. So this is the typical kind of output we get. If you are in our data set, we can also produce an ID label for you, or we can tell you your age, pose, gender, and all of that. And we use these things in different ways. Now, till the most recent system we delivered was just about a couple of weeks ago. Before that, we were using ultraface for everything, detection, alignment, fiducials, and then alignment and everything. But as part of the most recent data call, we got surveillance videos. It's called CS6, Challenge Data Set 6, which is not available to not for folks who are not in the program, but I can tell you a little bit about that. Really bad data set, very challenging data set, tiny faces. So we have to quickly design a DP SSD, we call it, Dynamic Pyramid SSD for face detection. Since the goal of this talk is not to dwell on the main algorithmic aspect of a face matcher, I'm going to just show you the structure. If you really want the details, you all have to take a flight and go to Munich and listen to my talk Saturday afternoon at one of the workshops. Of course, it works well. As you know, the plot has to be the top and the right, for it to make it to a publication. This one thing also is very interesting for computer vision. When I wrote papers in the early 80s, I just had my algorithm, my data set, everybody was happy. But now you have to have comparisons with half a dozen data sets and 8 different algorithms. And I don't think we really reproduce any of the other algorithms. We're just citing numbers from their tables. So that's something we have to think about. I think I like to say when we do research in image compression, if the PSNR, peak signal to noise ratio, was better by half a dB, it was a conference paper, 1 dB, it was a journal paper, 3 dB, you got an award. All right? So we're kind of in that thing. And in fact, when you are an area chair for CVPR or reviewers, you probably get a note saying, don't just look at the numbers, look at the ideas. Even if they're, the numbers are lower, look at the ideas and, take them. And it doesn't happen very often. Once in a while it happens. I mean, I was pleasantly surprised when we submitted a paper on domain adaptation, unsupervised domain adaptation to ICCV 2011, and my student has numbers like 19% on the office data. I said, are you kidding me? They're going to throw this thing away. But luckily they took it, So once in a while it happens. I think we need to think when we are reviewers, let's not just look at the numbers are important, but the methods are very important too. And I hope you don't mind me preaching. As an Indian, once you are 65, you can pretty much preach anything, I like to say one advantage of being an Indian, by just simply aging, you gain respect. I think it's probably true in some other cultures too, but it's definitely true in Indian culture. Once you are 65, it's like Seinfeld says, once you are 80, he's going to pull out of the driveway without looking left or right. Everybody else has to give way. So I kind of have that attitude, but I started doing it in 65. Okay, of course, when you do tiny faces, wider, thing is important, and so on. So it's interesting that, again, if your ultimate goal is detecting, of course, you can worry about detecting a 5 by 5, face. But if you really want to discriminate or verify, there's not much information in that, right? So you got to think about that. Anyway, so we know how to detect faces. We get the fiducials. We know aligning and so on. So then the question came, what kind of networks do we want to use? So we tried lots of networks. At one point, we had 14 networks, just doing all kinds of things. It's like 14 experts sitting on the table. Everybody is an expert in one aspect of the law, and then the case comes in, and then they make a judgment, right? So that's how we viewed it. Now, finally, we reduced down to just 2 networks. But you have to experiment with, this is the way it works now. Of course, it's 101. I like to say, I think ResNet 101 came from Microsoft Asia, I believe. If it had been an Indian lab, it would have been 108. But for Indians, 108 is the holy number. But or 1008, for that matter. 1008 will need too much data. So 108 would have been fine. But 101 is okay too, because in Indian tradition, whenever we give a gift, cash gift to nieces and nephews, we don't just give 100, we give 101. Just makes it slightly more than 100, right? Of course, when I do it in the US, they'll say, why are you giving 101? Just give me 100. No, 101 is what we do. So there is 101, and I don't mind that. Okay, so loss functions. As you know, in backpropagation, it's an optimization function, loss function. So softmax has been around. One of my students, star students, Rajiv Ranjan, said, well, I want to do a constrained L2 softmax function so that the features all lie on a hypersphere. The particular radius of the hypersphere is again, has to be learned from the data. And as you can see in these 2 spheres, the softmax is not giving a lot of separability among classes, whereas L2 softmax is better that way. And of course, anytime you have a loss function, if you have a multi-class problem, there is an underlying PDF, and the L2 softmax corresponds to the von Mises distribution and so on, and there are some parameters in the distribution that you can control for deciding between interclass and intraclass. I mean, that problem doesn't disappear, right? Interclass, intraclass. I think we try to address it in different ways using different methods, but that's a basic issue. So this is the architecture we put together, and these are the training data sets. Of course, we had collected our own data sets, so-called the universe data set, and we combined that with MSN1 and so on. I believe the universe data set's available for downloading. If not, please feel free to contact me, and I'll. Okay, so again, staying on this topic of building a face verifier and a matcher, these are the various data sets that came to us from this program. You have access to IJ, BA, BB, and BC, and you do not get the C series, CS1 through CS6. And as you can see, they had a lot of different tasks. The main task is, of course, the verification task, recognition task, and all the recognition tasks are open set. Okay, so it means the probe faces are not in the gallery. So it's a slightly more challenging situation. And then, task 9 is a situation where you have to do end-to-end, detect. Then when you have multiple faces in a picture, you're going to detect all the faces and sometimes non-faces, so you have to have the proper threshold to just get the faces and then match and so on. So the tasks get more and more complicated. So let me just give a very brief, next few slides will have these numbers, but as you can see, we are now talking about true acceptance rate at a false acceptance rate of 1 in a million. This IJBC data allows you to look at that region of far tar. As you know, when we have very small data sets, we never went below 1 in 10 power 3, 1 in 10 power 2. But 1 in a million, and if you are 80% accurate, it has some meaning in operational situations. And okay, so that is one thing I want to point out. As far as the recognition is concerned, you have 95% rank 1 and so on. And these are not your passport pictures or cell phone pictures. These are pictures from the wild. And so there's no control. You can look at IJBC to see how challenging those are. And of course, when you add the megaphase distractors and so on, the numbers will go down. If you have a million distractor, you still rank 1 is about 80%. And then open set identification in the wild. That means, there's, in the case, before the evaluation I showed before in the previous slide, one particular phase was chosen and then you had to match. Here, you just have to detect all the phases and so on. And UMD3C is the most recent version we submitted. So we are seeing, things like upper 90s consistently and on really difficult images. CS Infinity is a very, very difficult data set. So there's so much available, so I can now talk about 10 power minus 8 false acceptance rate. So I'm allowed to make only 1 in 100 million errors in verification, and when I say these two faces come from the same person, I'm accurate 70% of the time. Just 6 months ago, I was at 35%. So this is the thing that's happening right now. Things are moving too fast, and the data-driven thing is exciting. I like to say that it's like having donuts for breakfast, lunch, and dinner. You're always on the sugar high. But I think at some point you're going to come back and look for oatmeals and fruit. I'm waiting for that time, right? It's really too exciting. So, I can go on and show various plots. I think you get the picture. This is the CS6 is the most difficult one. Surveillance, video to video, video to single, video to multiple. The numbers come down. That you expect that. So by no means we can say this is a solved problem. Again, even here, while the data sets are difficult, when you really get to the most difficult data set of surveillance videos and so on, the performance still has to be improved. Well, that's so much for the excitement. Again, when problems are such, we can map data to labels, and if you have a lot of data, deep network is the way to go. If you don't, your competition will win. That's just the way it is. Now, does it mean we have really solved a vision problem? I don't think so, right? We still have a lot of other issues to worry about. First of all, main things that people are worried about now is the training data size. So learning with less labels, it's called LWLL. It's a new program that somebody is interested in. So how low can you go in terms of training data set, right? Now, if you're doing a simple statistical inference, linear statistical inference, and so on, we have some guidance about how much sample size we need in terms of confidence intervals and so on. Even if you're just learning the mean of IID Gaussian, or sigma square by n is the variance of the location estimator, so you know how as you go through the n increases, you know how much the variance decreases. Deep networks, 101 layers, nonlinears, we don't have any results like that. It's really a big problem. So that's one issue. The second issue is training. If you are training on some data set, sure, that the network is going to do well. What if I give a different training data set? The numbers go down, right? So domain adaptation. So can we design networks that have the domain adaptive behavior? Well, when you do regression, it's clear that regression is trying to find a map between the data and the output, right? That is what it was supposed to do. And suddenly you can't ask it to go and work on a totally different data set. There are some data sets which are maybe linearly related or something like that. There is some scope. but you can't just make it work on other data sets. And expecting it is like, teaching a kid English all the while and suddenly throwing some exams in French and say, hey, come on, do domain adaptation. It doesn't work that way. So whenever people say, oh, it doesn't work, I said, it's not supposed to work. Don't make it do things it was not trained to do. Okay? First you have to do something to it, right? Domain adaptation. So I'm going to talk a little bit about that. The third one, of course, is the famous Google picture. I think it's from Don Song's group. A stop sign, you put a few pixels, and then the autonomous vehicle is going to run over a 4-year-old kid and all that stuff. Sure. Again, if you live by data, you die by data. Period. Okay, so we should be careful when we kind of try to. I know it's all exciting to, say these things, but there is definitely, a reason why it can. If you have outlier, in fact, go back to 1979. Since somebody said I've been doing research since 1980, I might as well go back to 1979. There's a very nice paper on robust estimation of time series by Doug Martin, the professor at Washington Statistics Department, Journal of Royal Statistical Society, right? He'll show that if you have a time series estimation problem, you can add outliers at the same scale of the innovations that drive the time series, and you can be way off in terms of robust estimation. You can be way off. It doesn't have to be very large outlier because time series is a correlated data, right? So, when you have IID models, then we understand what the outliers are, and we can define robust estimators using redescending two-key functions, M estimators, generalized M estimators, and so forth. Some of that can be transferred to time series. But the difference is when you are in time series, the innovations, the outliers, very, very small outliers can cause havoc. Now, we are talking about 101 layer and with nonlinearities and so on. So who knows what's going to happen? So you have to, it's not surprising that it may have issues, but we can design some methods for making them secure, and I will discuss that. So these are the 3 problems I'll talk about. Of course, there is a lot of other work, and I don't have time to go over all the related works. And I was thinking, how do I justify not mentioning all of our friends' work? Sometimes I do, sometimes I don't, due to lack of time. I say this is a keynote. That means I'm giving you a key so that you can take note of things, right? So I can't get into too much detail. Now, the problem here is the following. I have already designed a network. I have 10 million data sets. I designed a network with 2 million. I still have the 8 million hanging around there, and I'm tempted to use them because I can do better by another 2% and things like that and get a CVPR paper. But then I say, who wants to do another 8 million? So suppose if I take 1,000 at a time, is there a way I can come up with a strategy for choosing just 10 out of those? Okay, for doing that, I need to have an idea of how well the method is working right now. Remember the curriculum learning idea that you slowly give, more and more complicated things for the child to learn. So we have a way of characterizing for a multi-class classifier the uncertainty in the decision the classifier makes. Because if the classifier is having hell of a difficulty, then I don't think we should give it more difficult samples, right? If a student is struggling with Calculus 101, I mean, we're not going to give Calculus 303 problem to the person. So you need to have an idea of measuring the performance of the classifier, and then if you are having a budget, for example, total of empty samples, and then I have K classes, I want to make sure the samples are chosen so that all the classes are represented. Even in a SVM, the bias, because of different number of samples in each class, is something that we have to worry about. That's the same thing is true here. So we want to be able to distribute that, and one way to do that would be come up with this kind of a criterion, something related to watershed algorithm, in information theory, and so on. And then we maintain a diversity of representations and so on. So basically the idea is to make an optimization problem. It's amazing to me that the last 5 years, optimization has become a core mathematical technique that we need in computer vision. Of course, regularization, showed us in the early 80s that that's important. Then it kind of disappeared, and then it has come back again. So, all computer vision students should learn optimization. Very, very important. Steve Boyd's book. Okay, so we put this and then come up with a way of choosing the best out of the next batch. So how does it work? Well, we have 2 parameters. One that says, I want the best samples that represent the class. The other one says, I want the best samples that separate the class. So you have control what you want to do in terms of these two parameters, the kind of regularization parameters, and we hand adjust them. And if we say I want the best samples that represent each class, then you see the beautiful pictures we have on the top, like, okay, let me see, like these guys, all very nice pictures. Whereas if I say I want to emphasize classes that are hard, that means they are in the border, and then you get all these crazy images that we have to deal with. So there is some intuitive behavior behind this method. And then we also do the thing about what are the samples that are chosen as we continue this optimization process. So in the early stages, you should, of course, choose nice, simple ones like this. And as we get better and better, this is what it chooses later on. And so as you can see, this is harder than this, and this is harder than this, and so forth. Anyway, I think this is iceberg, and this is not an iceberg. So we do make mistakes. So there is this idea of starting with simple examples and giving it harder and harder examples. Of course, this is harder than this, and et cetera, et cetera. So we kind of like this, and this is the kind of performance we get compared to random sampling and so on. I think we still are not there yet in terms of telling you that I can reach the same performance at a fraction of training data set. In fact, one of the recent efforts is we have to produce the same results for ImageNet kind of an application with number of training samples lowered by a factor of 1 million and things like that, 10 power 6 by a factor, right? So it's a very ambitious goal. So this problem is still open. There are many other methods available. Professor Favreau does semi-supervised learning, and Rene Vidal does low matrix factorization algorithm and so on. So that's an open problem, trying to get the results with a very small training data set. It's an unsolved problem, right? So we have to work on that. The next one is the domain adaptation. Now, what is the domain adaptation problem? We have known for decades that the training and the testing data are different. They come from different distributions. Because training data is what you do to design your classifiers, and then you build your classifier, put it in a box, and send it over somewhere else, and they're going to use it, and they're not going to use the same data that you have, right? So domain adaptation, became an issue sometime in, it's been there. Hal Domey, for example, my colleague at Maryland, did this for natural language processing in 2007. Of course, vision people were a little slow to get on that. Kate Sayanko and Trevor Durrell did this paper in ECCV 2010, a semi-supervised domain adaptation. So in the case of domain adaptation, we talk about source and target data. Source is where you have training data, you have labels. Target, you may or you may not have. If some of the target data has labels, then you call it semi-supervised. If none of them have labels, you call it unsupervised. But you assume that both source and target data are available at the same time. Well, that is domain adaptation. There is a new twist to it where you don't have the target data available, but just the source data available, so-called domain generalization. So we have some recent work on that, and I will very briefly mention it towards the end. So when Kate Sayanko had that semi-supervised, and then my student said, well, we should do the unsupervised version. Okay, so if you have an unsupervised problem, what's the best thing you can do in terms of designing a classifier? Well, PCA is good, isn't it? Because you don't need labels. If you think back to eigenfaces, you take all the faces, align them, and then build the eigenspace, and then get your coefficients. And if two pictures come, you want to match them, you just project on, get the coefficient. You don't need any ID information. So for unsupervised case, PCA is good. So the moment you have an unsupervised domain adaptation problem, my student said, sir, maybe we should take the PCA of the source, PCA of the target, and project them onto the manifold, because it's a Grassmannian manifold. And so now you can go along the Grassmannian and connect the source and the target data, and you can subsample it in between and create intermediate projections, basically subspace structures. And then anytime you want to match source and target, you can project them and create the long feature vector. Yeah, pretty reasonable idea. And so, it got an oral paper at ICCV in 2011. But the performance was slow. But since then, it has gotten better, right? So that's using manifolds. Of course, we have done using dictionaries and so forth. So there's a lot of this stuff going on. Now, what we thought we would do is, how do we use GANs for domain adaptation? Is there anybody here who has not used a GAN yet? Please raise your hand. Yeah, start tomorrow. Yeah, I don't know. Just to see, GAN came in 2014, Goodfellow's paper, right? Now in the last 4 years, there's just GANs everywhere. Okay, so that's not why I think we should be doing it, but it provides a very interesting approach. Well, what does the GAN do? I mean, it tries to, started as a data augmentation effort. It says, well, I have a generator, I have a discriminator, I have real data, and then I want to produce more real data. Well, fine. Then you start with the Gaussian vector, and then go to the discriminator and say, hey, I'm the real data. The discriminator is like a bank employee. He says, no, you're bringing a fake note, so go away. And then goes and does a better printer and better Xerox, better, et cetera, and so it tries to match the performance in terms of an optimization function and tries to produce data that looks like training data, right? So you start with a Gaussian thing, and then you have a real data, and then you have a mechanism, the fight between G and D. It's like a min-max game, and eventually when everything converges, you have the training data kind of model coming. The generative model learns it. Just replace the noise Gaussian with target data. Okay, so I have a source data, I have labels, but I also have a target data without labels, right? So now what I want to do is I want to find an embedding that shares the attributes or the characteristics of both source and target data. So once all of this happens in the classical GAN setup, then I will have a feature embedding, and then when the target data comes, I can run through it, and then I will have the class labels. So the source and the target are mediated using a GAN. So of course, when you go to GAN, you have the loss functions galore, right? So we have a CVPR 2018 spotlight paper, so I will ask you to, or request you to take a look at it. This is first the GAN, and then there is this conditional GAN, and then we use the AC GAN because in the original GAN, it's a binary issue, where real or fake. Now we need a source or target, but when we synthesize in G, we also have to synthesize class-specific generation, right? Because we have a multi-class problem. So that's why we use AC GAN. And these loss functions are all pretty standard, either cross-entropy loss or, the conditioned on the feature, or the real-fake discriminator loss. We have the cross-entropy loss because of the multi-class problem here. So, of course, we have to be careful that only source data has the label, target doesn't have. So the picture is like this. So I have two streams. The top stream is a classic feature embedding followed by DCNN and so on, and it is a standard one because we have source and we have the label, so we find the feature embedding. Now then we feed that whatever it learns into the bottom stream, which has the classic GAN setup. So the idea here is real fake as well as the class labels come out, and then we synthesize class consistent parents using this. So basically, when these guys converge, this F should have not only be sensitive to source, but it's also reasonably good for target, and then you throw it in here. Okay, so this is a very simple way to explain how you can do domain adaptation using GANs. Of course, we also have done semantic segmentation using it, where there is a real image, and then you have totally synthetic image, because synthetic image has labels with it, right? So you can mediate using that. So how does it work? Well, we've tried many different methods, and so this is a side to front face problem. So rank 1 gets a little better. And then we also tried the office, the famous office data that came from Kate Sanko. So if you look here, in 2012, this is where we were, 2012. These are the three domains, Amazon to webcam and DSLR to webcam, etc. And so slowly things get better, and then we have again slowly getting not close to saturation yet, but definitely improvements compared to what was here, right? So this is encouraging. And of course, you can see over the years we have done using manifolds. 2012, performance 55.6 for Amazon to webcam. Then when we did dictionaries in 2016, things got slightly better, and deep features, instead of dictionaries, we use them, things got better, and we use GANs, things are getting better. So for the same data set, same problem, by using these different methods that have happened since 2012, you can see that, again, deep networks plus GANs are producing good results. So one more reason why everybody should look into it, right? Okay, of course, every time you talk about deep networks, there's always somebody in the audience says, Professor, we have seen this picture of a stop sign with a few pixels misplaced and how it goes totally somewhere else, so what do you do? And oftentimes, people who are not in computer vision, they're all very fascinated by this. So you tell them, well, if you do data, if you have wrong data, you're going to have an issue with that. But more and more, we are looking at how to protect our deep networks, right? So the most recent work we have is this one that appeared in iClear in 2018. It's called Defense GAN. Well, we have a lot of interesting work going on. This has become a very hot area right now. Of course, there are many ways you can take care of it. Adversarial training, what does it do? Okay, I have some noisy things. I'm going to add the noisy things as part of my training so I get better. Well, we don't know how much noise we can tolerate, right? That's the whole thing. There is, in fact, right from the 80s, we have all said, those of us who use neural networks, it's always good to add some noisy samples because it builds resistance. It's like in India, we used to say snake charmers. Every day take a small amount of venom so that finally when a cobra bites them, they're still okay because they have developed immunity to it. But, nobody knows how much venom they should take. If you take a little bit more, you may just disappear before a snake bites you. So that's a problem learning from noise because we do not know how much noise in the data is good still, so we can still learn, right? If you take a class from a professor who uses very inconsistent notations every time, and then, we're all going to be confused. So anyway, that's one way to do it. It's still open. We don't know how much noise and so on. And the second one is magnet, which is autoencoder, to reproduce the input image. And I think these methods, magnet and the ones I'm going to talk about, Defense GAN, we try to sanitize the bad image. What happens is we learn again so that it can reproduce the good data very well. And anytime an adversarial input comes, we see whether that lies in the range of the generator. And if it is not, then we don't let it into the classifier. So sanitization, you can view it as somewhat denoising and so on. So this has to do with making the input image behave better. Of course, there is another work which we have recently done, is under review, which is the L2 softmax. What we found is the L2 softmax that we use for building deep networks also has some adversarial robustness because of the compactness of the features and so on. So one of my students developed a concept known as compact convolution, which applies the L2 softmax and normalization at each step and so forth. So that is changing the network structure to take care of the adversarial inputs. So this is basically how it looks. Again, we have a GAN structure. The simple idea is to see if the input is within the range of the generator, and if it is, and you can have a threshold to actually spot which is the bad output. As you know, it's an outlier detection kind of an approach. And we did this Defense GAN, and then we said, yeah, it's okay, you do a paper, and then you move on and go to the next paper. But then, Dr. Carlini, Nick Carlini in Google, and David Wagner, they have this paper in ICML 2018. I think it's one of the best paper awards. I'm going to finish in 2 minutes. Where they go and try to break all the networks. I thought, computer vision has our own problems. Do we really need people to come after us trying to break our networks? Well, anyway, if you put a network up, they want to break it. So they broke 6 of the networks in iClear. And the 7th one is ours, Defense GAN. They couldn't completely kill it. When we did the MNIST, they will go and attack it. We were still 55% accurate. Whereas most other networks in iClear were all 0. One of them was 17. I'm going to show the tables. So I told Nick in an email, hey, you have wounded us but not killed us, right? So so that's encouraging. Also, there's a very nice paper I've written here in the bottom. It's a beautiful analysis of classifiers. the thing is adversarially vulnerable for any classifier, right? So they kind of say the strategy we use, the so-called nearest neighbor strategy, to checking whether the adversarial input is in the range of G is a good strategy. So, that's good. Anyway, you can detect attacks. White and black attacks we can handle. Some of the earlier methods will do one and not the other. So you can see, I'm sorry if the fine print is really fine print here. As you can see, defense GAN in the block, the hard dark characters is better than when no defense, right? So that's basically what we want to show. So we are still working on this problem, and we're kind of excited that we have, because when you tell people that you're building a system with all deep networks, the first thing they give you is the Google example of a stop sign. So you got to kind of protect yourself by saying, no, we are also working on securing our networks. So this is what I was talking about, Carlini-Wagner attacks, obfuscated gradients paper. So this is our work, and so we are still 55%. So when Nick now writes, he says he broke 6 completely, and ours he broke partially. So if I'm limping as I walk out of the stage, that's because he broke my legs. But my heart is beating. That's what's important. Okay, so there's a lot more work that I can talk to you about. We don't have time. But luckily, everything is an archive these days. So that's a new thing that we have to live with. And yeah, we've done a lot of things related to this talk and so on. So deep networks are here to stay, whether you like it or not, but just view it as another set of features. There's nothing wrong in it. SIFT is the kind of features we all like at some point. Deep features, you can always keep them in your toolbox and see what happens to it. It has its issues because it comes from, learning, and no learning is perfect. But it's great. High school kids are very excited. Every year I have a couple of high school kids. They want to do this, they want to do that. They say, download Cafe and run this and run that, and they're very excited. It looks like it's working, and one kid even wrote a paper with me on a workshop at ICCV 2015. She had an AP, advanced placement in statistics, has scored 5. She tells me, I want to work on a regression problem. I said, 17-year-old kid, right? Okay. I said, okay, look at FGNet, download Cafe, estimate the face age. She came within 2 years or something like that, so we wrote a paper, and so this is all good. More importantly, easily portable software. Those of us who have worked in this field for 3-4 decades will build something in our lab, and we thought it was technology transition if it worked on the other room. Because obviously that person had a different software environment, different computer, nothing worked. Now I can do something on this with 4 networks and this and that. I can throw it to you. You will be able to run it in half an hour. And people are not emphasizing that enough. That's why every company wants to do deep network and so on, because it's very easy to make things work and put in a box, okay? That's good. Of course, all the other problems, you all know about them, so I don't have to belabor much on that. I'm going to stop here. Thank you very much for your patience. This is the last talk. I hope it was worth your wait. And if you have any questions, I'm happy to answer them. Thank you very much.
So we have a time for a few questions.
As you said, they're all very tired. Indeed. Apparently there were no questions also in the morning oral sessions.
Let me ask one question first, while audiences are taking time to think.
Sure.
So I think one of the topics that you mentioned in your talk is to generate data sets by neural network, and also those generated data sets are meant to be used to enforce recognition network. So we generate data by neural network, also use them to retrain our recognition network to improve accuracy or performance of our classifier, for instance. But then, obviously, these two are very important components. But is there a good possibility that we can do them in a joint way? So I mean, like, if we just generate, but not knowing enough about classification side, then these generation data points are not necessarily helpful, most effective to boost up recognition accuracy. But what I'm worried is that, I mean, if you attempt to learn those two parts together in a simultaneous way, then there might be some issues like in computational efficiency, complexity, also algorithm complexity. There is no guarantee that iterating those two networks might as well converge in a continuous way. So do you have some comments on this?
I think when we do data, we have training data set, and if you are using GAN to develop more, we still have to provide some proofs that the data generated by GAN is, probability distribution is the same as the training data. But right now we are doing it all in a very deterministic way, and so I think we need to develop, I actually wrote it on my board a couple of weeks ago, I want a probabilistic GANs. Maybe somebody's already doing it, I'm not aware of. How do I guarantee that the data we generate from GANs is closer to the PDF of the training data within some KL measure and things like that? Okay, so then I'm not too worried about the classifier and so on. I'm just trying to generate more data, right? So that's one way I would approach that, in terms of ensuring that the data generation scheme has some probabilistic interpretation underlying that, so it can behave like the training data. And then you generate more training data, hopefully the performance will be better. Yeah.
So any questions from audience? I think Lama might stay a bit further at the conference site. So if you have a question but shy to ask a question, then feel free to come and ask questions in person directly to Lama.
Right. Except that if you ask question here, the answer is free. If you ask outside, it may cost you some money. Sorry.
Maybe if I throw one more question before ending the session. So
clever, very clever.
Are advocating the use of deep neural network in our research, right? So saying that it might be just another feature.
Yeah.
Why don't use it if it's really helpful in practical sense?
Right.
But then, are there not some negative aspects like doing something on top of neural network? Does it not limit our somehow novelty or the scope of our inventions, etc.?
Yeah, but I think we still have a lot of open problems. For example, geometry is not encoded that well in deep networks, right? And the 3D representations, illumination models, we still have all of those old issues again. There's no claim that the deep features are robust to any of these variations. So we still have a lot of work to do. But all I'm saying is, from some problems, we are seeing good performance. So you just can, try to figure it out, why it's working well, and if anything better can be done. My feeling is if you want to do theoretical analysis, you may do such analysis for something that looks like it's working, rather than just doing other things. So I think we have plenty of scope in terms of theory for deep networks, which is beginning, at the very beginning stage. So it's good. I view it as physicists used to have these linear accelerators. They just built it and then they've discovered all kinds of new particles and started writing theories about why they are there. So I'm not claiming deep networks are such exotic things, but we have a machine we can run, right? If you work in one of those big companies, you probably have a whole basement full of GPUs, and so you can really address some very, very large-scale visual recognition problems and kind of understand. Before we couldn't do it, So remember my PhD from Purdue, 1981, I was sharing a PDP 1145 with 30 other PhD students. Just imagine, so you had to work during weekends and late nights. And I was only able to process 32 by 32 picture. And I did 2D FFT. That's all I could do in terms of Markov random fields and so on. But right now we have so much power and a lot of data. So I think it's a slightly different situation. We should be skeptical, but we should try. Right? Because, as I said, in all the face recognition works we have done since 1992, I cannot imagine getting the performance on these data sets on anything I've done before 2014. So that's a fact.
Thank you very much, Lama. So let's thank Lama for a wonderful keynote once again.